Yeah, hello folks. Today we have Maharshi, who is an alumni of IIIT, who's going to be presenting a talk on his work. Yeah.
Oh yeah, so hi and thanks for inviting. So I'm going to talk about certification of local quantum systems, and so this is it's based on like a few papers here listed here, and it's joint work with several people from several domains like optimization theory, and quantum foundations, and a wide range of backgrounds. And so before that, a brief statement about me. So I was in IIIT long time back in 2010 to 15 in a 5-year dual degree course. My supervisors were Indranil and Laltu sir, and then I moved to Singapore for my PhD at the Center for Quantum Technologies. So yeah, this is the picture on the right. So this is a CQT building here, and it's a place where a lot of like people working on quantum in different aspects, like even like experimental to theory in physics or theory in like computer science. A lot of very varying background people work there. So I went there, and so I was supervised by Miklo Santa and Troy Lee, and I got my PhD last year, like towards the end, and then from then December onwards, I've been like officially affiliated to Mie University in Japan. Uh, yeah, I'm just waiting for like my visas and stuff to arrive so that we can go there. At the moment, I'm still in Singapore. So what I work on broadly is basically quantum computing, various aspects of quantum computing, theoretical aspects. Uh, in general, a lot of in general like theoretical computer science stuff, such as optimization theory, game theory, and I also like working on quantum foundations, um, and like basically mixing all these things together in some sense. And we will also see some quantum foundations in this talk today. So the talk outline, so the plan is as follows. So basically, I'll tell you what do I mean by device certification. Um, and then I have to introduce like a framework for quantum contextuality, which goes by this name, Cabello-Severini-Winter CSW framework. Uh, this is the framework which is like common and like, to all the three like work that I mentioned earlier. And I briefly will talk about this so that the background is clear. Then I'll go into the first type of certification schemes called self-testing. I'll define what do I mean by self-testing in the local setup, and then we'll give you the self-testing statements for odd cycle and anti-odd cycle graphs. Then I'll talk about the second certification scheme, which is the dimension witness, and we'll formulate it and like explain how tools from like rank constrained SDPs can help in studying these kind of dimension witnesses. And the main contribution here would be like we will see a family of dimension witnesses for arbitrary high dimension. Okay, so first we will give you a brief idea about what is device certification. So I mean the best analogy I can give you is something if in the classical world is like suppose you have written a computer program P to compute for some function f, okay, and so I mean with most likely what happens is this program is a little bit buggy, and that's something that you want to figure out, like is p of x is equal to f of x for every input instance x or not. uh, I mean, and furthermore, you might have this kind of setup where you write this program P and then you just give this program in a black box to somebody else to test it. Like they cannot maybe even look inside the program, but they can just give some input X and evaluate it at this particular X. So, so obviously, I mean, if you have to like know whether it is buggy, like bugs free or not, you have to do it for every instance, but that is obviously will take a lot of time. But you can of course study things like say you can fix a time something reasonable. For example, the time approximately same as the time to actually uh, solve, like actually execute this program P, maybe fix it to that. And then maybe what you want to maybe guarantee is like some kind of probabilistic statements, or maybe something like you want to say estimate the fraction of input instances which are incorrect, something like that. So people have studied all those kind of things, and in this is completely classical. And so there is a like this very strong parallel in the quantum thing as well. So in quantum, you would have like instead like some quantum states and measurements. I am assuming everybody is familiar with this basics. Uh, and so which is like, so these quantum systems are usually prepared by untrusted sources. Or even if it is not untrusted, I mean, in today's world, I mean, we are not there, like technologically, we have not reached that point where we like produce a very high like fidelity, very good quality quantum systems. So it's a very crucial point to like benchmark these quantum systems. And so the goal is to like, yeah, we want to like verify or figure out some properties of these quantum states. Uh, and also it's kind of like this black box. It's similar to this black box fashion. Like we we do not make any assumptions on this quantum state and measurements. By looking at some classical data, we want to say something about it. Yeah, so that's the general setup actually. So we perform some measurements on these quantum states and then collect some experimental statistics. And from these statistics, we want to figure out some properties of these states or measurements. So like a little bit more formally, I mean, so the data, the form of the data that you get will depend upon in which scenario you're working under. So here in this slide, I'm just giving an example of this non-local scenario, or this is a scenario that you encounter if you're familiar with non-local games, or maybe Bell inequalities and all this stuff. So like you have two parties here, Alice and Bob. They are like in uh, different laboratories and like space like separated, and they so they cannot communicate. That's the restriction. And so they are given some input X and Y respectively from some finite set, and they give some output A and B again from some finite set. So in this case, the data that you would like to collect are these conditional probabilities, this probability of getting output A and B given input X and Y. Okay, so you get this bunch of statistics, and and then you can basically, you want to do something about with those data. So if you are familiar with like Bell inequalities, so they are so those are defined in terms of these conditional probabilities here. There's also this coefficient SABXY. And here on the, so basically you take some linear combinations of these probabilities. That's the, that's the idea of these Bell inequalities. And here on the right-hand side, this SC is the largest possible classical value of this expression over all possible classical strategies, okay? Uh, However, when you're using quantum, you can do something better. You can share some entangled states between them. And so which is this psi AB here. And also you can measure them, and you can calculate, then this probability PAB given XY will be given by this. This is the usual Bond rule that we know of. And so like with this, in quantum, you can sometimes get a value which violates such kind of Bell inequalities. So one such case is the CHSH experiment, where this XYAB are this binary, have this binary strings 0 and 1, and this SABXY is of this following form, where it's 1 if the XOR of the outputs is equal to the logical AND of the inputs, and 0 otherwise. So yeah, so this is just an example of such a scenario. And in general, so the question is that if you collect such data, P of AB given XY, can we figure out something about the underlying quantum systems? So we will come back to this example also a little bit later. And yeah, this is just to give you an idea of what's about to come. Yeah, so next we jump on to, so this is like a non-local scenario, right? And a lot of these certification schemes have been proposed for non-local scenarios in the past. So today's talk, it will be mostly about local scenarios, and for which we would require a slightly different type of inequalities, which is known as the contextuality inequalities. And for that, I would like to introduce this framework, CSW framework. So for the next 3-4 slides, I'll be talking about this one. Okay, so here we will start off with some measurement events, okay? Like think about them as like some input and output tuples. So E1 to say there are n of them. And then we will say that like a pair of events are exclusive if they cannot happen together, okay? For example, I mean, you do a measurement, you get some outcome A, and then you do the same measurement. So that is the event first, 1. And then the event 2 is that you do the same measurement and get a different outcome. So these two events cannot happen together, for example, okay? So these two, we will call them an exclusive events. And then corresponding to that, we will construct this exclusivity graph, Gx, which will comprise of n vertices. And we will draw an like edge between I and j if this events ei and ej are exclusive. Okay. Now we will like assign some like probabilities to these nodes in the graph. So pi will be assigned to vertex I, where p is this n dimensional vector, and we will call it as a behavior. And we have to have this additional, so this rule that pi plus pj is at most 1 whenever I and j will share an edge between them. Okay. So this is basically telling you that if your events are exclusive, then the sum pi plus pj must be at most 1. Okay.
Hey, the example you gave for the exclusive events, I mean, did you just give an example or you want to say that that is true?
Uh,
I
the one that by an example, you mean when I said you measure for a given measurement, you have 2 different outcomes, that one? Or
Right, yeah, that one.
yeah, it's like one of the examples where these 2 events are like mutually exclusive. You cannot, any event which cannot happen together, that's the idea.
An event here is like, say, a measurement, comma, an outcome. Like, say, if I measure with, I mean, if I do an X measurement, I get a spin up. That is it.
That's right. That's right. I mean, in general, you can have like multiple such measurements, not just one single, but you
Okay.
measure something and then to this, and you measure something with that. So 2 measurements, and like there are 2 separate outcomes. So the entire
Okay,
thing can be
so
called as an event. So
I see.
yeah, what I said was one of the examples.
So, but what you said could happen, right? Like, unless we're fixing a state as well. Like, I could say have a measurement and have one outcome that can be an event. And oh, okay, both cannot.
Not at the same time. Yeah, in
I,
different thing. Yeah,
I see.
yeah.
One minute, why would I ever measure at the same time? Uh, okay, can you give me an example of non-exclusive events?
For example, I mean, you do two different measurements, okay? Then, I mean, they can happen at the same time, right? So this event is probably you're thinking in terms of you're thinking in terms of the like what state collapsing or stuff like that. But this is just a classical way of looking at events, okay? So I'm saying tomorrow it is going to either rain or it is not going to rain, kind of like that. So these two events cannot happen together in that sense. So like if you measure something, you will either get this 0 or get 1. You cannot have both of them together. It's a classical way of thinking. There's nothing quantum happening at the moment at all. Is it clear or like? So I'm just saying.
I think I'm still okay.
Yeah, go on.
Perhaps when you move on and maybe say something
okay.
else, would be clear. Yeah.
Right. But yeah, I mean like. Yeah. Okay. Yeah. But yeah, this is what I. Yeah. This is what I kind of meant. Like. You should keep the thing in mind. Yeah. Like it's like. Yeah, I think that example is the good example. Like this rain and no rain day. I mean, those are like totally exclusive events, right? You cannot have both of them happening together. So yeah, think about it like in that sense. Okay, so now depending upon, so we were assigning these values, right, to these vertices of this graph. Now, depending upon which theories you are working in, you will put additional constraint to this assignment. So suppose you are working in this deterministic non-contextual theories, then like in addition to this Pi plus Pj is at most 1 for an edge, ij, we must have that this values must be binaries, 0 or 1 exactly, not in this range 0 and 1 real interval, but exactly 0 and 1. So this is basically like you have some predetermined values for these events. So what it means is that it's just if you think about it a little bit, it's nothing but the characteristic vectors of the stable set of this graph. So like stable sets is nothing but this subset of vertices such that like no two of them are like connected to each other. Okay, so this deterministic non-contextual behaviors are essentially this characteristic vectors of this stable set of this graph. Now, if suppose you take a convex hull of all these deterministic non-contextual behaviors, you end up with something what you call as a non-contextual behavior. Okay, so it's basically like a randomization over all these deterministic behaviors. So now it was, so this was observed in the CSW paper in 2014 that this polytope of this non-contextual behavior is in this set called the stab of this graph. So stab of this graph is a well-studied combinatorial object, which is nothing but the convex hull of all the stable sets. Okay, so by the trivial like logic, what I gave earlier, that tells you like why they are same, and this was just formalized in this paper. Then from here we move on to the next theory, which is the quantum theory. We will say that now this behavior P, we will say that it is a quantum if we have a state psi and projectors pi 1 to pi n, such that you can write this Pi as this inner product psi pi I psi for every I. And whenever there's an edge between I and j, then trace of pi I pi j is 0. Okay. So just like the classical set or the non-contextual set was shown to be equal to some well-studied combinatorial like set called the stab. Here also, the quantum behaviors can be expressed in terms of another well-studied object, which is the theta body. Okay, so there is this non-contextual set of behaviors, and then there's a super super class of this quantum behaviors, and here which is characterized by this theta body. So what is that? So like we say that X is in this theta body of a graph G, if there exists a positive semi-definite matrix X of size n+1, such that you can embed this X vector in the following way. On the diagonal of this X matrix, you will have the X. You will also have to put the X on the top row, and the top left entry 0, 0 will be 1. And whenever there's an edge between I and j, the corresponding xij entry will be 0. So like if you want to figure out if x is in this theta body of this graph or not, that's basically equivalent to SDP feasibility program, okay? So this was the other observation in the CSW paper, that the set of quantum behaviors is in this larger set, which is this theta body. Okay, this is also not too difficult to see. I mean, if you're familiar with this, like this gram decomposition, so you just take this gram vectors of this matrix X. So there'll be like n+1 of them. And then if you do a little bit of scaling, then basically you will recover all these vectors here, this psi and this pi1 to pi n. Or equivalently, if you start with these a quantum realization, then you can show that the behavior that you generate is in the theta body. So it's kind of, it's not too hard to show that. So yeah, so now let me just define some graph invariants, and yeah, that would be useful. So the size of the largest stable set is called this independence number, and it's denoted by this alpha. The Dova's theta number is basically you want to maximize the one norm of this x, where x belongs to the theta body of G. Okay. So written in another way is basically like you want to sum up the diagonal entries from 1 to n of this matrix X, such that I just rewrote those constraints from the previous slide here. Yeah. And so basically this is an SDP, right? So yeah. And then there is this third quantity, which is this chromatic number. So it's the minimum number of colors needed to color the vertices such that no two vertex shading and edge have the same color. Okay, and we will denote it by this sky. So there's this very famous theorem known as the sandwich theorem, because this, so we have this relation alpha of G is less than equal to theta of G is less than equal to this a chromatic number of the complement of this graph. So while the first and the third one are like NB hard to compute, okay, the second, the middle one here is the SDP, and therefore it has a polynomial time solution. So that's why it was like I mean, people love this kind of theorem, like love this, and like a lot of work has been done on Loas theta, and yeah, Loas theta in general is a very interesting like object. I mean, whenever people study semi-definite programming, this is one of the first thing that they really encounter, the Loas theta SDP. So yeah, this is also of like you can know for independent learning. So this is a very interesting theorem. So if you recall, yeah, so we will see that. So we saw that this alpha is the, yeah, we will see it the next slide here when we define what is a non-contextual inequality. So non-contextual inequality is basically the facets of this non-contextual polytope. Okay, that is like we take some linear combinations of these components of this behavior vector Pi, where this P belongs to the classical set or the non-contextual set, this stab of this graph. And here, this value is at most this weighted independence number of the graph. I mean, if you just, for convenience, you can just take W's to be all ones. And then this summation of PI is at most the independence number of the graph. And similarly, if you replace this behavior from a classical to a quantum set here, theta body of this graph, then this is, as we saw from the previous slide, it is the lowest theta number of this graph. So in this previous, so this one constitutes the classical and this one constitutes the quantum. Okay, so now let's look at one of the simplest of non-contextuality inequalities, which is one of the first one to be introduced, was known as this KCBS N inequalities, named after these 4 people who came up with it. So this this corresponds to the inequality where the underlying graph, this GX, is this odd n cycle, where n is like some odd n greater than or equal to 5. Okay. So, like for example, if you look at the simplest one, say n equal to 5, which is the pentagon, the classical value would be the alpha, the independence number of that pentagon, which is, you can clearly see, it's just 2, right? And but if you compute the lowest theta of that, or the quantum value equivalently, that comes out to be square root of 5. So this is a simplest of all these KCBS simplest of non-contextual inequalities, where there is a classical quantum gap there. And yeah, so just to tell you here, like this square root 5, here this umbrella that you see here is like it's basically like if you so basically you look at the quantum realization which achieves this largest value of square root 5. So there is a state psi and this projectors pi 1 to pi 2, pi 3, pi 4, pi 5. So the red ones are the projectors and the blue here is the state. So it happens that like if the relative angles are some specific form in this umbrella structure, then you can achieve a square root 5 violation. Later we will see that like this is the only configuration which achieves this square root 5. Okay. So with that, we go on to like self-testing, which is the first like scheme. So so this is the general idea is, again, as I said, like we want to certify underlying quantum states from measurement statistics and have been studied in the non-local setting. So the CHSH is a self-test for this 2-qubit maximally entangled states. Okay, so like if you perform the CHSH test and you achieve the Cyrilson bound. Cyrilson bound is basically the largest quantum value that you can achieve. And it for that CHSH, it is 2 root 2. If you achieve this largest value, then you can for sure guarantee that the underlying state must be this Bell state up to some local isometry. Okay, by that I mean like there is some isometries V1 tensor V2, which takes this psi AB to some junk state times tensored with your maximally entangled state in 2 qubits. Okay. So these are the kind of statements which guarantees that the self-testing statement gives you. Like you just, all you need to do is like get this classical data. And once you achieve those, like once those data satisfies some bounds like 2 root 2 or whatever in this case, then you can guarantee something about the internal structure of this quantum system. So they have a wide application, this self-testing. They have been used for random number generation, delegated computing, verifying computation like For example, I mean, you have so if, I mean, if you want to, so I mean, yeah, this is a like a long-standing problem. Like if there are like two provers and one verifier, then this problem becomes slightly easier. Then there in those situations you can use self-testing using like these two non-local self-testing schemes for such verification. Um, and then this self-testing is also used in like several recent complexity theoretic proofs also, like this MIP star is R equal to RE. Yeah, so basically it has a lot of applications. Okay, so let us define now what do we mean by self-testing in this non-contextuality inequality scenario. Okay, so similar to the non-local scenario, we say that this non-contextual inequality, we take this inequality, non-contextual inequality, and we say that this inequality self-tests the system U0 to UN. So here U0 is supposed to be the state and U1 to UN are the projectors. And we say that it self-tests the system if firstly this quantum realization here achieves the maximum value, which is the lowest theta. And for any other ensemble, UI primes, which also achieves this lowest theta, there exists some isometry which can take this UI to the UI primes, the same V, of course, for every I, 0 to n. So that's basically very similar to the analogous definition in this, which we saw in the previous non-local scenario. There is also a robust version of this, like because of experimental imperfections. I mean, you must, it's very useful to have robust statements. So we say that this inequality is an epsilon R robust self-test. If firstly it self-tests this realization UI, and for any other realization UI primes, which like achieves the epsilon suboptimal value, there exists some isometry which will take this UIs to the UI primes up to some small error like order of epsilon to the power of R. Okay, so it's a natural like generalization of the previous case.
So, hey, so I'm slightly lost, but I just want
Yeah.
to get a
Yeah,
general idea of what's going on.
yeah,
So,
yeah, sure.
yeah, so why do we say, when we say self-test, why are we including the projectors as well as the state?
Yeah, I mean, yeah. So here, it is. It depends upon the context. You are saying that, like, okay, so um, so that in the literature, there are sometimes you will find like you just self-test a particular state, or you just self-test like some measurements. But in this case, I mean, even in the Bell case, actually, if I go back. So this statement is like is the half the statement. I didn't write the entire thing. This also tells you that there exist isometries which takes there's a canonical measurements which achieves this CHSH maximum bound, right? Those X, Z, and this Hadamard and all this stuff. So so there's an analogous statement for the measurements as well. So in our case, it's very important actually to take the state and the measurement together, because if you just take the state, that then that's trivial, right? There'll always be some isometry which takes one vector to the other vector. But what we are saying is that there's one single isometry V which takes the whole bunch. So basically you're saying something about the geometry. Okay, so you are saying the relative geometry of all these vectors together. So if you remember this umbrella structure that I was telling you, that for the case of pentagon, there is this umbrella structure which achieves the maximum. What this kind of self-testing statement would tell you is that like if you up to some rotations of this umbrella in some axis, it will always be an umbrella. That's the point. So here it is important to like take both state and measurements together. Yeah. Is it clear?
So like just to confirm, so like basically it's like saying you can use the same set of measurements to test like effectively any system that satisfies the inequality, right? Just basically up to isometry.
I mean, if it achieves the quantum maximum, you
Yeah,
also
all the systems that achieve the maximum, like you can test them using the same set of like measurements up to
uh,
isometry.
like okay, this is as follows. Like, okay, if this UIs, this set of system achieves the maximum, then yeah, then then it's a candidate for such a test. Yeah.
Right.
If it doesn't, then yeah,
Yeah.
we have to look at some other inequality, something like that.
Right. Okay.
Okay, so if there are any other question I can take, or maybe I can jump into the results. Okay. Okay, so the first result is that like what I was telling you, for this any odd n, you take any odd n cycles, n greater than 5, greater than equal to 5, then this KCBS n equality is a epsilon half robust self-test for the canonical ensemble. By canonical ensemble, I mean the umbrella configuration that I mentioned. Okay, and I'll just give a brief idea, this proof sketch of what's happening. So firstly, we want like to show that the behavior, the quantum behavior, which achieves the maxima, for example, in that pentagon case, the root 5, there's a unique behavior which achieves. That's what we want to show. And to show that, what we do is that we show something even more general. We show that the lowest hit SDP corresponding to the pentagon graph has a unique solution X star. Okay. Of course, if it is unique, then the diagonal will be unique. Right? So then what we show for the robust case is that suppose there is some other matrix X tilde which achieves this epsilon suboptimal violation, then the difference between X star and this X tilde in Frobenius norm is some order of epsilon. Okay. And then finally, this last step is simple, and we show that if two PSD matrices are epsilon close in Frobenius distance, then their gram decompositions are order of root epsilon close in L2 norm. So this is why the half factor is coming in the previous slide. And yeah, I mean, this gram decompositions, why are they? So if you recall, I said the gram decomposition of this matrix X corresponds to the quantum state and the measurements. Okay. So this last step is anyways simple, and this first two, they require some tools from semi-definite programming literature. So I'll just tell you the first one, and that might be useful for you in any of your work. So yeah, I'll just tell you the theorem that is useful. So this is a generic theorem which tells you when do you know that a SDP solution is unique. Okay. So you must have heard about this duality theory, and so you have in general, a primal SDP looks like this following. So you have some linear objective functions and some with some affine constraints, AI X. So here the bracket are the trace inner product. So we have this AIX equal to BI, and there are M such constraints, and this X belongs to some positive semi-definite cone. And the dual of it looks like you want to minimize the inner product between this B and Y vector such that this matrix here is positive semi-definite. Okay, so there's this theorem by Alizadeh et al., which tells you that if you take Z, this matrix here, suppose you take some dual optimal matrix here, And then you look at the set of linear constraints, linear equations as follows: mz equal to 0, then the trace inner product of mai, where I is equal to 1 to m, all of them equal to 0. You look at this system of linear equations, and you automatically see firstly that m equal to 0 is a trivial solution, right? If you put m equal to 0, all of these satisfies. But the thing is that if m is equal to 0 is the only solution, that is, there are no other like non-trivial solutions, then the primal SDP here will be having a unique optimal solution. Okay, so by studying the dual optimal here, we can say something about the uniqueness of the primal. Okay, yeah, and just to know, like, we will call such a Z which satisfies this kind of like algebraic conditions, we will call them as a dual non-degenerate optimal solution. So as you can see, a lot of these things boil down to like figuring out what this dual, like if you can prove dual non-degeneracy, then a lot of these things can be solved. So so for example, I mean, if you write the dual for the Loas theta, I mean, you can write it, you can check it out that it is basically of like this form. Here, this EIJ matrices are the standard matrices where you have like half and half on the entry IJ and JI, and everything else is a 0. Okay, and EII is basically having 1 on the II element, and everything is 0. Okay, so for example, like for the cycles, like odd cycles, this is the claim that Zn is given by this matrix is the optimal dual solution. Okay, I mean, the proof sketch is pretty simple. I can go through it very quickly. I mean, of course, if you want to say something is optimal, dual optimal, you would like to show that it's just you want to show that firstly it's a feasible thing. So you put such you just replace take these t lambdas and mu ij's in this equation to these values, plug it in, and you will see that it satisfies. All that you need to show is that this Z is a positive semi-definite matrix. And for that, you can use the standard, some techniques like Schur's complement and stuff like that. Yeah, I mean, I can skip all these parts. These are some simple linear algebraic stuff. Yeah, so basically, what helps us in this case really is that we can characterize. So you can see, like when you're trying to prove such results, at the end of the day, you have to talk about some eigenvectors. Like you have to deal with the spectrum of this adjacency matrix of this cycles. Okay, so in the case of cycles, because it's a circulant matrix, its eigenvalues are like well characterized. I mean, yeah, you can look that up. So those are well characterized, and you can have a very nice. So the proof and everything, you can work it out. In general, this is a problem for like if you give any random graph, the spectrum is like not at all easy to characterize, and therefore this problem is a little hard in general. But in this case, it turns out to be there's a lot of symmetry and stuff which you can exploit and prove such result. Okay. Okay. I mean, and then the next step, once you found the dual optimal solution, you have to show that it is a non-degenerate solution as well. For that, like if you look at all the constraints, the set of linear equations I mentioned in that earlier slide. So here, this M is that matrix of variables. So if you look at in this case, so you have all these constraints, right? MA1 to AM. So in this case, if you just evaluate those equations, you find that the M matrix must have some particular structure which is given by this. So like whenever there's an edge, whenever there's an edge between I and J, there should be a 0 and so on and so forth. And the final equation is this M, this matrix, the product of this equal to 0. And from that, you have to conclude that all these entries here, this M1 to, I guess, M10 is 0. And here it's just a demonstration that this actually works out. So when I say 0, 0 here, I mean when you multiply the 0th row here by the 0th column here, so it basically tells you that M1, the M1 plus M2 all the way up to M5 is equal to 0. Yeah, so trace of this matrix is 0 in other words. And similarly, you can if you look at 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, and so forth, you get some set of equations, and from that it eventually works out. Okay, so eventually you can show that all of these variables are must be 0. So this M5 is equal to 0. So these kind of arguments you can generalize, and that's kind of the idea behind showing that such a dual non-degenerate solution, such a dual solution is also a non-degenerate solution. Okay, so with that, I'll talk about the second result. So this is about extending this previous result to other graphs, and in general, in particular, the complement of the cycle. Okay, so that too admits a epsilon half robust self-test. And we will see why this is a case interesting in a while. So, okay, so here the main issue, like the main idea is that it's okay. It again comes down to showing, like, figuring out what the dual is and all the stuff. In this case, it turns out to be if you see, okay, there are like 4 programs here, right? So there is a primal corresponding to the cycle Cn. There is this dual of the cycle Cn. There is the primal of this complement of the cycle Cn, and there's a dual for this program. And we want to say something for this, and it turns out to be it's hard to come up with a dual directly, but the thing is, we can relate this thing to the primal solution for the cycles. And for the primal solution for cycles, we know them explicitly, right? Because we studied those gram vectors and all corresponding to the umbrella structure. And because we know that, we can relate it to the dual here. And that is what this theorem basically tells you. I'll just quickly, it basically tells you that if X here is this primal, here is this B0 is the gram matrix of these vectors V0 to Vn for this solution here. Then if you want to compute this Z star, this is this Z star here, then all you need to do is scale this up with this factor here and flip the sign of the first entry. Then the matrix that you obtain here is the dual for this anti-cycle. Okay. So okay. So, and the rest of the proofs are like similar in nature. Okay, and so I'll not talk about it. But why is this case more interesting? Okay. One thing I didn't mention was, like, in the earlier this cycle case, this for this. So it doesn't matter like which n you choose. For any n greater than or equal to 5, you can always achieve the quantum maxima, which is the Lorentz theta, in dimension 3. So I showed that picture, this umbrella structure, right? So that was a 3-dimensional figure, but it for any n, like for 7, 9, anything, there will be another umbrella structure in 3 dimension which achieves the maxima. So suppose you want to self-test 3 dimension, then it is fine. But suppose you want to self-test some higher dimensional systems, this will not be sufficient. But it turns out that this anti-cycle has this nice property which is given by this claim here that for any odd n greater than or equal to 5, the dimension in which this quantum realizations corresponding to the anti-n cycle graph achieves the maximum lower theta is like n minus 2. So it grows with n. So this kind of gives you the like this kind of helps you to certify arbitrary high quantum dimensions. The idea here is like basically to do with like the primal solution, right? The primal solution here is of this form. I will not go into the details here, but the point is that, as I told you, if you know this primal solution, the primal solution, the primal matrix here, X star, is related to the quantum state and measurements, right? By those gram vectors. So if you can lower bound the rank of such a matrix, you can lower bound the dimension in which it achieves the maxima here. So in particular, what we do is just lower bound the rank of this submatrix here. That's the idea. Okay. So what about general graphs? Like we talked about cycles and anti-cycles. And like the question is now, is it always true for in general graphs or not? So the general recipe is like the following. And most of this diagram that we see here, it's basically this follows from Alizade's the paper I referred to earlier. So they already talk about such like ideas. And so the main algorithm is like you start with some primal dual optimal solution, X star Y star, sorry, X star Z star. Then you check for this two conditions. One of them is non-degeneracy that I talked about. The other thing is strict complementarity. That is like if the duality gap is 0, and then if so duality gap is 0, as in like trace of X star Y star X star Z star is 0, and the rank of X star plus rank of Z star is equal to n, or like the full rank or not. So like that is known as a strict complementarity condition. So if it happens that if it is not strict complementary and if it is non-degenerate, then those things, then it is then X star is unique. Otherwise, we will have to like maybe start with another another Z star and restart this process. Otherwise, on the other spectrum, on the other hand, if strict complementary doesn't hold, and if it is non-degenerate, then it is unique. But if it is non-degenerate, then it is not unique. So there is a way to actually show that X star is not unique. Okay. So, and it turns out that if you look at some graphs, you can show that there exist the graphs such as this and shown here, for which this X star is not unique. So such graphs you cannot self-test. So so that's kind of interesting. Like, and of course, this is one of the open problems that can we characterize exactly the class of graphs for which you can show self-testing results? And probably it's not so easy for the reasons like it's hard to know the spectrum and all, right? So that's the main issue. But there are many easier problems. Maybe show some things, some theorems like if G is self-testable, is the complement of G also self-testable or not? Or maybe something like vertex transitivity can help or not. The second open problem is finding explicit robustness bounds. Like we mentioned it in terms of order of epsilon, right? But like computing the exact like constants and all are sometimes useful in like practical purposes. So yeah, that would be interesting. Then yeah, large gaps, like self-testing graphs which have large gaps between the quantum and the classical value is also of practical like usefulness, because if the value between these are too small, then it might be hard to experimentally actually do these experiments and show these results. And yeah, last one is kind of like a generic question, like all these, can these kind of self-testing statements be useful in verification of quantum computation or something like that in the local schemes or not? Okay. Okay, so with that, I'll move on to the next, and I guess this is the last section of this verification scheme. So far we were looking at one aspect of certification, like, okay, and here this is the other aspect of certification. It's called, so we want to, here the idea is that we want to look at this, like we have this data, and from this data we want to say something about the dimensions of these quantum systems. Okay, slightly different notion here. So here, like looking at the example earlier, like if you again you have this non-local like setup, and we can analogously look at d-dimensional Bell inequalities here. So in the previous slide, we have this additional restriction here, the superscript d and the superscript d here. So what that means that here this behavior, this p of ab given xy superscript d comes from such a quantum realization psi and these measurements, where this psi belongs to this Hilbert space of size d. Okay, and so here so basically you are restricting it to a class of quantum systems. So that is the restriction here. So an SDQ is basically the largest such violation possible when you're restricting it to the class of this d-dimensional Hilbert space. Now, the basic idea of quantum dimension witness is the following. Like if you take such an inequality so suppose you do some experiments such as like this non-local experiments in the lab, and you observe some violation in this inequality, okay? Then it automatically implies that the underlying quantum system must have dimensions greater than or equal to like d+1. So that's a simple idea. Like if you can violate such an inequality, you can lower bound the dimension. And similar to self-testing, like dimension witnesses also have a lot of use. Okay, here the references are, so here I was talking about dimension witness in the non-local sense scenario, but it has also been studied in various other scenarios like the prepare and measure. This is the non-local scenario was studied here in this Brunner paper or Navascu's paper here. Dimension witness for high dimensional entanglement testing, right? It was used in this work. And then dimension witness has also been studied in this contextuality framework in this work. And what I'm going to talk about now is basically some sort of a generalization of the last one, okay? Where we study the contextuality using this graph-theoretic approach. Okay, so like as before, now we were looking at these behaviors. We will now just put additional constraint, like the additional dimension constraint on them. Okay, so suppose you have like now instead we will call a behavior as d quantum if you can write these pi as again as before psi pi I psi and trace of pi I pi j 0 whenever I and j have an edge, except that these are now like d-dimensional quantum state and projectors. Also, we will call such this pi1 to pi n, which satisfies this relations pi1 trace of pi I pi j 0 whenever there's an edge as a d-dimensional orthonormal representation of G. Okay. Okay, some definition. So what is an orthogonal rank? Orthogonal rank is given by R0, RO rather, is a minimum D such that there exists a D-dimensional orthonormal representation of this graph. Okay, so I mean, if you must have some like you cannot have an orthonormal representation in say 1 dimension or 2 dimension. Only once you achieve a certain dimension, then only you can satisfy these constraints. This pi I pi j is equal to 0. Okay, and the next idea is the next definition is the lowest rank given by RL, and it comes from this SDP here. So here, what you see is the usual lowest SDP that we talked about earlier, except that here is a rank constraint here. The rank of X is at most D. And that is given by this superscript D, the theta superscript D, okay? So the lowest rank is the minimum D for which the lowest theta number is equal to this theta D, okay? So it is now from these definitions, it is obvious the following kind of inequality, I mean, following thing is holds, because as you increase the like rank of the solution, you are increasing the feasibility set, and therefore the value will be increasing, right? So if you look at the theta restricted to R, the orthogonal rank, the RO, that is the least, and then it keeps growing all the way up to the lowest theta lowest rank, which is equal to the lowest theta. Okay, so this inequality is like suggests you that you can actually construct dimension witness if you using this kind of idea. What I mean by that is like you look at such a rank constraint non-contextuality inequality, summation of pi is at most theta d of g, where this p belongs to the quantum set. And if your experiments give a violation, the violation of this inequality, then it implies that the quantum system must have dimension t plus 1. Yeah, so before that, I mean, like, one thing I must tell you, of course, like, in case you don't know that, like, these kind of programs here, like, we know semi-definite programs are polynomial time solvable, but when you have this additional rank constraint to a SDP, that makes the program hard. I mean, NP, like, in general, it's NP hard. I mean, the best way of understanding is that, like, if you heard about this max cut, a max cut can be written as like a semi-definite program with an additional rank constraint that the rank of the solution must be equal to 1. Okay, so I mean, by this reduction, I mean, these kind of problems in general, rank constrained semi-definite problems are hard. And therefore, to calculate these values, theta d, that will, in general, you cannot do such things. And that is the major challenge. Like how do you actually come up, like, how do you know there's a violation? Like, how do you compute such values? And you have to do it for arbitrary high dimension. So that's the challenge. So this is the result of, like, the last result I'll talk about. We identify a class of graphs which allows us to certify arbitrarily high quantum dimensions. Okay. Just to begin, like, how we even began to search for such graphs is by, like, playing around with, like doing some numerical simulations to begin with, to understand what's happening. So we would so here, what this algorithm that's written, it's like, I mean, you can actually apply it to several other places, so that's why it's also useful. This algorithm is basically telling you how can you find low rank solutions of such rank constrained SDPs. Okay, so as I told you, it's hard to solve such a problem, but like, can you do some heuristic and stuff like that. So here the idea is kind of like the seesaw method, if you know what that is. Or in literature, they're also known as this alternate minimization. Okay, so like suppose there is some nonlinear optimization which is happening, that would be hard to deal with, right? Then what you do is let you fix some part of the optimization, make that optimization a linear optimization or something that you can solve, and then minimize over that. And in the next round, you fix the other thing and minimize over the other second aspect. So a similar idea was used here. So here you can see that we are solving some like two SDPs simultaneously in each iteration here. There are like two SDPs. The step 4 and 5 is one SDP, and step 6 and 7 is the other SDP. The first SDP is trying to satisfy all the like constraints of the Lorentz theta, and the second SDP is trying to fix the rank of the solution to the preferred rank that you want the solution to be. Okay, so if you run this for several times, there's no guarantee, of course, because it's a heuristic, but in many of these small cases that we figured out that it works very well. For example, these graphs here that you see, so these are well motivated graphs for like some, they occur in this contextuality literature, but I won't go into the details, but for our purpose, there be some whatever graph it is. And this program gives you, of course, it gives you only a lower bound on this rank constraint theta value. Okay, so if you fix the rank to be 3, for example, in this graph, you get a lower bound of 3.333. And for 4, you get 3.47, which is equal to the Lorentz theta of this graph. So of course, you cannot go beyond this. What is hard to show, although, is that this is also an optimal, like it's at most. Okay, I mean, we have now what this program is like. If you run this program several times, starting from random initial. So here you see there's a random matrix. Okay, so there's some randomness in this program. So so you start from various different places, and it can happen that it gets stuck in like local minimas. Okay, so but the point is that if you do it for like many times and you still cannot cross this bound like border 3.333, then it kind of gives you a numerical evidence that maybe this is indeed the maximum. It's hard to prove, of course, but it gives you an indication. So such kind of like intuitions helped us build the graph that we will talk about later on the next slide. And again, similarly for this graph here, there's a similar structure here for different values of like this dimension 4, 5, 6, 7. You see there is a level structure. As you increase the rank, you get a value progressively higher. To prove the upper direction, again, I repeat, that is the difficult part. So of course, actually this problem here, I mean, I believe we tried a little bit to show this is also an optimal above, but it's hard actually to show that this is indeed optimal. But we do prove such results in this family of graphs, which we call as family of kites. These graphs so have this basic. This is how we define this graph. So we call the graph as a k-kite, and it has like 2k plus 1 vertices, v1 to v2k plus 1. The first k vertices form a fully connected graph. Okay. Then for this next layer, so there are 3 layers. The first layer is this connected graph. The second layer, which is like v k plus 1 to v2k, that is like this vertex vi is connected to vertex vi plus k. Okay, and then there is this third layer, which is comprising of one node v2k plus 1, and it is connected to all the vertices in the second layer. To just give you an example, it turns out the pentagon is like this, is the first element of this set. It is this 2 kite. So here you start with the complete graph, which is just the edge here, 1, 2. Then in the second layer, you have this 3, which is connected to 1, 4, which is connected to 2. And in the third layer, this 5 is connected to all the elements in the second layer. More instructive example would be this 1, 2, and 3. For the 3 kites, you start with a triangle, complete graph. Then in the second layer, you have 4 connected to 1, 5 connected to 2, 6 connected to 3. And the third layer is this node 7, which is connected to 5, 4, and 6. So, and you can generalize this. You see the logic, you can generalize it to all K. And the point is that if you, so we, for C5, we already noticed this gap classical quantum. Here also you will notice this alpha of this guy is like 3, and the lowest there is some gap here. In fact, you can show that this theta of K kite is strictly greater than K for any K greater than or equal to 5. Okay. And here are the results that I'll just briefly tell you. Firstly, the independence number of this family K kite is K, which is not very, this is very, very easy to show. Then you show that the orthogonal rank, which is like the minimum dimension where there exists orthonormal representation, you can show that you can construct an orthonormal representation in dimension K. And then this is the main result, that these values, this rank restricted values, which I told you was NP hard in general to compute, for these classes of families of graphs, this value, this theta K for K kite is at most K. Okay. Now this gives you the whole recipe, all the ingredients. What it means, this theorem, what it means is that suppose you violate this, you take this inequality, Pi is at most the K is the independent, the classical value, right? Or the in this case, whatever, this is just also equal to this value. So suppose you violate this inequality, it means that the underlying so where P is taken from this quantum set, and now if you violate this inequality, it means that the underlying system must have been larger than K, strictly larger than K in this particular, it's K plus 1. Okay, so that's the whole idea, like how studying these kind of rank restricted SDP values can all help you figure out construct dimension witnesses. So this idea generalizes, as I said, and like you can construct dimension witnesses for arbitrary high dimension. Some problems like finding generic upper bounds for like lowest theta. For, I mean, of course, in general, for any SDPs, it is NP hard, but is there any hope for figuring out some analytical or at least some upper bounds on the lowest rank restricted lowest theta values for for this lowest theta SDP specifically? Maybe there are some ideas. Then find noise robust dimension witnesses, which is basically like some large value gap between the alpha and the, or like, yeah, some gap, there should be some gap between the two levels. That's what I was talking about. That would help in experimental like verifications. And finally is more like an open-ended questions. Like I talked about several scenarios, non-local, prepare and measure, and all the stuff. So maybe developing a general graph-theoretic framework to analyze and like unify all these approaches of dimension witnessing. That could be an interesting idea. Like maybe this approach, this graph-theoretic approach, can unify all of these scenarios. Yeah, that could be an interesting question. Okay, yeah, so that is actually all. And yeah, I would, yeah, if there are any questions, I would love to hear.
Yeah, thanks a lot for the
Yeah.
talk. It was really nice.
Thanks.
Okay, just wait for a minute for questions. Okay, I guess I'll stop the recording then.